All right, class, so today we're going to start chapter 7, and this PowerPoint is going to cover section 7.1 and 7.3. So this chapter talks quite a bit about inferential statistics, okay? So we were using descriptive statistics in chapter 2, and now we're going to use inferential statistics. And what we do when we're using inferential statistics is we're using them to infer about a population, okay? So it's important to remember that when you have a population, it has a parameter, and when you take a sample, that's going to have a statistic, okay? So if you aren't familiar with those concepts, go back to chapter 2 and take a peek. There are two major applications of inferential statistics. One is we're going to estimate a value of a population parameter. So that's what we're going to do in this chapter. And then in the next chapter, we're going to form a conclusion about a population parameter. In chapter 7, we're going to learn to estimate the population mean. Now, we can do this if our standard deviation, remember sigma stands for our standard deviation. So we can do this whether our standard deviation is known or whether our standard deviation is unknown. And as long as our sample size, remember N is representative of our sample size, or if our population is normal. Okay, so these are when we can estimate the population mean. We also are going to take a look at population proportions, okay, and population variances. So let's go ahead and say what we're going to assume in this chapter. So in this chapter, we're going to assume that we're dealing with a simple random sample. We know our standard deviation, and the population is normally distributed, or our sample size is greater than 30. These are going to be our assumptions. So when we're estimating a population mean, okay, we're going to take a sample statistic that we have found and use that to approximate a population parameter. There are two kinds of estimators. We can do a point estimation and interval estimation. A point estimate is when we use a single value to approximate a population parameter. This is when we would use the sample mean to estimate the population mean. That's about it. So if I wanted to say estimate a population parameter, so the mean height of people is 5'4". If I do conduct a sample and I found that the mean height of people, say in my statistics class, was 5'4", then we could use that to assume the population mean. But here's the thing. Is the true population, we talked about this a little bit in class on last Thursday, is the true population gonna have the same mean as the population of my statistics class? And everybody shook their head no. That's when we want to look at an interval estimate. That's gonna be the most important. So an interval estimate uses a range of values that is likely to contain the true value of a population parameter. So as before, I could have said the average height of a person's 5'4". Now I could say the average height of a person is between 5 foot and 5'8". That's going to contain our true population mean. That would be our interval. And we're going to look at how we calculate those. We're also going to refer to this interval as our confidence interval, because how wide that interval is determines how confident we are that the true population parameter is within that interval. So let's talk about critical values. Before we move on into our theory of confidence intervals, we got to talk about a new symbol and how to compute some specified values. So this symbol is Z sub alpha divided by 2. Okay? These are called critical values. Remember that Z sub alpha 2 is the z-score from chapter 6. Okay, so if you aren't familiar with how to find a z-score, go ahead and review that in chapter 6. So we begin with an alpha. Okay, this alpha specifies an area under our normal curve, and the value of alpha is closely related to our confidence interval. So if I have a normal curve, okay, I tried. Okay, and I want to find the 95% confidence interval. That means I have 0.95 area, right? I am 95% confident our true population mean is within this area right here. But what's left over? Here I have 0.95, so what's left over is 0.05. However, we need to divide this by alpha divided by 2, okay? And we need to divide it by 2 because remember, a normal curve is symmetrical. So over here, if I take 0.05 and divide it by 2, I would have 0.025 and 0.025. And in order to figure out what values we have right here, we have to find the z-score associated with these values. So remember that alpha sub 2 is going to be the area to the left and right of each of these lines below, kind of like I drew on the last slide. And to locate z sub alpha 2, we find the z value along the horizontal axis, so how many standard deviations we are away from the mean, right? Remember, that's what z values stand for. We're going to find that. So, friendly reminder, alpha is going to be the area in both tails of a normal curve, and we need to divide them by 2. Now, because of symmetry, z alpha is going to be the area over here. And negative z alpha will be the area that has alpha sub 2 to the left of this. So next we're going to set up a table for 3 very common values of alpha and z sub alpha 2. We want to make sure we keep this table handy when we're working on the problems for section 7.2 and 7.3. So it's important to note that when we're calculating a confidence interval, we never want that confidence interval to be less than 90%, right? If I said I was 80% confident about something, you wouldn't feel very confident about that, would you? So our main values we're going to have is a confidence interval of 99%. So the area would be, under my normal curve, 0.99. And that would give us an alpha of 0.01, because alpha plus my confidence interval is always going to equal 1, right? That gives us everything under a normal curve. And the area under a normal curve is always 1. So we're going to start with alpha to be 0.01. We're constructing a 99% confidence interval. We divide each side by 2. So that means I'm going to have 0.05 area in each tail. And we need to find the z-scores that have our desired area to the left and right using reverse lookups on our z-table. So here I have to figure out what is my z-table value. If I go on my z-table, I will see that my z-table value is negative 2.575. So that means I am negative 2.575 standard deviations from my mean. Now, it's going to be the opposite for our other side over here. Now I have 0.005. But remember, when I look up a value in a z-table, it gives me the area to the left of my z-table. So that means this area over here is 0.995. If I look that up in a z-table, I would find a z-table value of 2.575. So whereas here I have 2.575, over here I had negative 2.575. They're going to be the same, but one's going to be negative and one's going to be positive. They are always going to match. That's one way to check your answer. If they do not match, you made a mistake. So we say that z sub alpha is 2.575, or the critical value is 2.575. So here's our table. So we've got alpha for 0.01. Here's our z sub alpha, or our critical value, also known as critical value. And then we have our alpha. So if alpha is 0.01, we're constructing a 99% confidence interval. If alpha is 0.05, what confidence interval do we think we are finding? Remembering that alpha plus our confidence interval have to equal 1. So 0.05 is going to give us our 95% confidence interval. And 0.10, that's going to give us our 90% confidence interval. Remember, we never want our confidence intervals to be less than 90%. So let's keep them moving and find our critical z-values. I should finish spelling that word. For our 95% confidence interval. So now let's take alpha to be 0.05. We divide it by 2. Now 0.05 is the area in blue right here. So to the left of the z-value we want. And that means we're going to have 0.9750 in the area to the left of the z-value we want, right? Over all of this, right here under this, what was supposed to look like a bracket, is 0.9750. So we're going to look up these z values in our z table, and we're going to get negative 1.96 and 1.96. Remember, these need to match, but one's negative and one's positive. Okay? So now we know our critical value. This is it. Our critical value is 1.96. And because we're constructing our 95% confidence interval, the area in white is 0.95. All right, so now we have, for our 99% confidence interval, we have a critical value of 2.575. And for our 95% confidence interval, we have a critical value of 1.96. Last but not least, let's take a look at finding our critical value for our 90% confidence interval. So again, we start with alpha. We divide that by 2, okay? So we have 0.05 over here, and then our area to the left of our second z-value is 0.95. But the area in here is 0.90, right? Because this is our 90% confidence interval. So I go to the z-table and I look up, okay, what's the z-score for an area of 0.05? And that's going to be negative 1.645 and positive 1.645 for an area of 0.95. So we've found our 90% confidence interval. So here's our final table. This might be a good thing to copy down into your notebook or save. You can download all these PowerPoints from Schoology. So again, like I said, keep it available. So let's consider alpha equals 0.05. Okay? As you can see, we've shaded 0.05 of the entire curve. So how much is left unshaded? This area is going to be 0.95 or 95%. Okay? This is the middle 95. And we've seen this before, right? We had our 68, 95, 99.7 rule that we learned in chapter 5 or 6. That means that within my first standard deviation, I have 68% of the data. Within 2 standard deviations, I have 95% of the data. And within 3 standard deviations, I would have 99.7% of the data. However, okay, wait, it says I have 0.95 within negative 1.96 and 1.96 standard deviations. That's okay, right? We were rounding. It's an empirical rule, and it was an estimate. So now we're going to use 1.96. So let's find some confidence intervals. So let's guess what temperature it is outside right now. Don't look it up, just guess. I'm going to say it's 55. I'm recording this on March 19th, and it's rainy, but it's warm. Now, how sure are you that you got it exactly correct? Oof, I'm not super confident. I would say maybe like 40% confident. So let's say I was 40% confident. Now let's give you some wiggle room. Now let's say your answer's within 52 degrees. So I guessed it was 55 degrees. Now I could say, okay, it's between 53 degrees because I have 2 degrees less and 57 degrees. I feel more confident about that. I actually think it's a lot warmer than 55 at this moment. Now, what if I had a wiggle room of 5 degrees? How confident would I feel if I could say it's between 50 degrees, which is 5 less than 55, and 60 degrees? Now I feel pretty darn confident. Because what if it's 58? I wouldn't have been in this interval, but it would be in this one. How about 15 degrees? Wow, that's a really wide span. That means it would be anywhere between 40 degrees and 70 degrees. Gosh, I wish it was 70 degrees. But now I'm 100% confident, right? I'm 100% confident, personally, that the temperature is within this range. Oops. All right, let's erase that so we can see what I just posted. Technical difficulties. All right, so as my interval for my guess got larger, I became more and more confident that I was correct. The same is going to be true when we're constructing intervals for population means and population proportions. Okay? When we guessed if it was exactly correct and I said it was 55 degrees, that was a point estimate. When I gave myself some wiggle room, these were interval estimates. The idea behind a confidence interval is this. When we want to estimate a population mean, right? This is my population mean. Based on a sample mean, right? That's when we have an X with a bar. Oops. We need to estimate our true population mean with an interval whose center is our sample mean. So hence we get a sample and we compute a sample statistic, so a sample mean, and then we can use our data to estimate our population mean. However, our statistic came from a simple random sample, so I can't be 100% that my population mean and my sample statistic are equal. So we need some wiggle room, okay? That's when we're going to calculate how confident we are and how close our population mean is to our sample proportion. The less wiggle room, the less confident. So we're going to have less little wiggle room for a 90% confidence interval than we would for a 95% confidence interval, than we would for a 99% confidence interval, okay? And the size of the interval is dependent upon what you mean when you say likely. Let's go into that. Confidence intervals. So the basic concept's really simple. We're going to take a sample, we'll get a statistic. The statistic gives us a point estimate, a guess for for our population parameter, that's mu. And it's unlikely to be exactly correct, so we want to create some wiggle room. And we want to say that mu is an element of an interval where we take our sample mean minus something and our sample mean plus something. It depends how big we wanted our wiggle room to be. In the temperature example, we had a wiggle room of 2 degrees, 5 degrees, and 15 degrees. And we got more and more confident as this got bigger. So here, now instead of having, we could say our mean is somewhere in between this interval. So 2 factors affect the size of our wiggle room, the size of our sample. So the larger our sample, the more confident we can be that our sample mean is closer to the actual population mean, mu. And again, this should make sense. The larger the sample is, the more informed our initial guess is, right? I would feel more confident if I was looking at the average heights of everybody at Fontbonne versus if I was looking at the average heights of everyone in my statistics class, because that would be a much larger sample. Next, how confident or certain we want to be that our interval does contain our population mean, the larger the interval must be. This is called the law of how confident or sure we want to be. It's also called the level of confidence or our degree of confidence. So what do we replace that question mark with? We're going to calculate it with E, where E, we're going to replace it with E, where E is going to stand for error, right? So we're going to look for a wiggle room of the form x bar, which is our sample mean, minus our error, to x bar plus our error, right? That means x bar, if we were on a number line, would be right in the middle. And then I've got x bar minus E over here, and x bar, so our sample mean, plus E over here. And this is the formula for E when we know our standard deviation and are estimating our population mean. It's going to be Z sub alpha divided by 2, so that's going to be our confidence interval level. We made a table of those, times sigma over the square root of n, where sigmas are standard deviation. And remember, we divided by the square root of n's when we were looking at the distribution of sample means. Here's some things that affect our error bound, okay? So since n is in the denominator of how we calculate our error bound, let me rewrite this real quick so we have it. Since n is in the denominator, my error bound is going to decrease if n decreases. So that means the value we subtract from our sample mean will be smaller, and hence we'll have a smaller interval and better estimate for mu. So the larger the sample size, the smaller the interval. And you can get that from looking at the equation. Next, notice that we have our critical value for Z alpha in the formula, okay? If alpha changes, Z alpha changes, okay? The critical value is connected to how much of the area we want unshaded in the middle of the normal curve, right? That was going to be 90, so 0.90, 0.95 for our 95% confidence interval, or 0.99 for our 99% confidence interval. So when we construct a confidence interval, we specify a degree of confidence first, and then construct the confidence interval for that degree of confidence. The table on our next slide is going to show the relationship between the level of confidence and our critical values. So, like I said earlier, we're 90% confident. We've got an alpha of 10 and a critical value of 1.645. We're 95% confident. We have an alpha of 0.05 and a critical value of 1.96. When we construct a 99% confidence interval, we have an alpha of 0.01 and a critical value of 2.575. So this is how all of these things relate. So a 95% confidence interval, again, will have an alpha of 0.05 and its critical value is 1.96. And our sample mean is centered in the middle, 95% of data. So as our confidence level increases, so does alpha 2. Looking at the formula for error bound, we can see that as alpha 2 increases, so does our error bound. So if we want higher levels of confidence, we're going to have a bigger z. Hence, the value of E will increase, and thus the size of our confidence interval will increase. All of this is to show the mechanical results of what you noticed when we played the temperature guessing game, right? As our sample got bigger and bigger, as our error bound, when we were guessing temperature, got bigger and bigger, you felt more confident that you had guessed the temperature correctly. But our interval also grew as well. Okay. So let's work out a problem. I want to compute a 99% confidence interval for a population based on a sample of 50 with a mean of 60 and a standard deviation of 3. So first we're going to calculate our error bound. Our error bound is our z sub alpha 2 times sigma divided by the square root of n. I know that the critical value for z sub alpha 2, in this case our alpha was 0.01. So alpha divided by 2 was 0.005. And when we looked that up in the z table, we found a z-score of 2.575. Our standard deviation is 3, and our sample size was 50. So I found my error to be 1.09. Now I can compute that confidence interval. I'm going to do that by taking my sample mean minus my error and my sample mean plus my error. So 60 minus 1.09, comma 60 plus 1.09 gives me this confidence interval. This is our 99% confidence interval. So we would say the 99% confidence interval is 58.91 to 61.09. Here's another example where we have our sample consists of 75 TV sets, so that's our population mean. And the replacement times of those TV sets have a mean of 8.2 years and a standard deviation of 1.1 years. So I want to calculate a 90% confidence interval, right? This is the standard deviation for this is the z alpha critical for a 90% confidence interval. We would take 1.645 times 1.1 over the square root of 75. And you see I have a much bigger sample and a much wider confidence interval. So a much lower confidence interval, a much lower z-score. So we would get an error of 2.09. I take my sample mean of 8.2 years and I add and subtract our error bound. That means I get an interval of 7.99 to 8.409. So I'd say we are 90% confident that a TV bought in this time frame will last between 7.99 and 8.409 years. Now here's another question. What if we don't know our standard deviation? This is often the case in the real world, okay? If we don't know the mean, how can we know what our standard deviation is? It's important to realize that what we are doing in the classroom will often assume we know our parameters. This is so that we can see what is happening even though we do not know the parameters. We will wait until section 7.4, that video should be coming to you guys shortly, to work out cases where our standard deviation is unknown. First off, let's talk about some notation mistakes real quick. Students often make notational mistakes. Remember that z sub alpha divided by 2 is a z value, okay? And it's a number along the horizontal axis of our normal curve, right? And this value, alpha divided by 2, is the area, which we can also write as a probability, under the normal curve. It's really important, too, to make sure you know how to interpret a confidence interval. The interpretation of a confidence interval is sometimes hard to understand. So after you construct a 99% confidence interval, students often make the following mistake. They state that the probability that our mu, our population mean, will be inside the confidence interval is 0.99. And that's not the case. That's not what the 99% represents. It does not deal with the probability that mu will lie within the confidence interval. So then what does a 99% confidence interval mean? Okay, if you were to repeat the process of finding our 99% confidence interval over and over and over again, okay, so taking a sample of a fixed size, computing our sample mean, and then finding our error and getting the confidence level, then 99% of those confidence levels would contain mu. So if I was to repeat the above process with 100 different samples of the same size, then 99 of those would contain the true population mean. It can also be interpreted this manner. We have 99% confidence that the mean of our population lies within the confidence interval we have found. In this case, the word confidence is loaded with statistical meaning. Another easy way to see that this is not a 99% chance of being correct is the following, okay? It's very important to note that confidence interval is calculated from sample data. If you have bad data to start, your confidence interval will not fix it. This is why we can not say that we're 99% sure the population mean is in the interval. The term confidence in a statistical setting has a different meaning, okay? We're only counting for the fact that the statistic was from random sampling, right? And not everything random will still give us a perfect representative sample. Okay, consider the TV sets example. By random chance, our sample could have more TVs that required replacement sooner than average. This is what the confidence level is accounting for and nothing else. A simple way we can show this is maybe we accidentally wrote down all the repair dates wrong, so we had bad data to begin with. Then our confidence interval would not lead us to an interval with a 99% chance to contain our mean. So, in summary, we will use z sub alpha divided by 2 to find our error bound, as long as the population is normally distributed and we know our standard deviation. Or we can still use our z sub alpha divided by 2 to find, otherwise known as our critical value, to find our error bound. Even if the population is not normally distributed, but we know our standard deviation and our sample size n is greater than 30. Sometimes we want to determine how large a sample we must gather in order to guarantee our error is within certain limits. So, for example, we might be asked to find out how many students must we sample if we want to estimate the Fontbonne student body's GPA to within 0.5 points and we want 99% confidence. We can work backwards. Here's the formula. This is just our formula for E, solve for N, okay? And you will have to remember to always round up to the nearest whole person or items. No half people, no half houses or things like that. So our sample size will be our critical value times our standard deviation divided by our desired error bound squared. And in this case, we get to pick what our error bound will be. So let's say we want to estimate with 95% confidence that the mean salaries of statistics professors. You want to be within 1,000 of the true salary, and you can assume our standard deviation is $20,000. How large should N be? In other words, how many statistics professors do I need to survey? So I would take 1.96, which is the critical value for a 95% confidence interval, times our standard deviation, which we said was 20,000. I want to be within $1,000, so this becomes my error bound, and I square it. That gives me 1,536.64. So we would need to round up to 1,537. So in order to have a sample with an error bound of 1,000, I would need to survey 1,537 statistics professors. That's a lot of statistics professors. So I hope by now you are more confident about confidence intervals. I will be posting the rest of the Chapter 7 videos shortly.